that Michael, Vivian, Scott, and the whole crew chose this to be the destination for your event. We're really honored that you're here. I'm going to start with a little commercial on lunch. That's right, the pizza's actually not free. Okay? So I'm going to keep it short and sweet though, right? 5 minutes, 6 minutes max. So here, ByteHands, our company, we've been around for about 10 years. We're probably best known for our TikTok. We go to market as our product brands. We're about 110,000 employees now, 160,000 if you include contractors. It's a pretty historical growth considering 2 years ago, we were only 30,000 people.
For services, so I think a lot, some of you might already be asking, what's the relationship between WebAssembly and microservices, because they seem like two different things, right? WebAssembly sounds like something that's used in the web. It actually is originated in the web. However, we are using it on the server side. So for those of you guys who are old enough, like I am, we remember a lot of technology has gone through this journey that moves from the front end to the back end. Java was the most famous WebAssembly container compared with Linux container. Is that WebAssembly is not a general OS environment, so you cannot take an existing Linux application and just plug it into WebAssembly. You can't do that. You have to write it service, which is really the typical three-tier architecture that everybody knows. However, there's a difference. So remember the figure I showed early on. So 3 Linux containers, 3 tiers. Now it's also 3 tiers. However, in the middle, instead of a Linux container, we have those green thing. It becomes a WebAssembly container, right? A WASM Edge container. It's now applications. The application server used to be 100 megabytes, right? That's here. It's 3 megabytes here because it's Rust application compiled to WebAssembly. So I want to show you what this Rust application actually looks like. This is the font is kind of big, but this is the entire application. So this is the main method. So this main method, if you are familiar with Rust Tokyo, you can see it does 2 things. The first is to build up the database connection pool. It's a MySQL connection pool. It connects to the database. Okay? And the second is to start a HTTP server that listens on a port. So the messaging queue could be Kafka or Red Panda. And then the middleware or the application is actually listening for that for events in that server, right? In that messaging queue. And when it sees a new message, it processes it and then put into the database. There's a ton of applications for that. It's essentially the database ETL work. That's all the data lake has to do that. So we here. I wouldn't show you the I can show you the code actually. So if I show you the code, it's very similar to the one that I've just showed you. So there's a main method here. The main method is even shorter, right? So it's passing the database URL, which is the database on the back end. It's passing the Kafka URL, which is the front end, and that's and then it has all those service methods that turns the Kafka. So it has 3 containers. The first is the middleware. It's what we call ETL Kafka, and it's 3 megabytes. Again, it's 3 megabytes. That's all there is. It's an entire application. And then the thing the application depends on, MariaDB, again, it's backend database. It's 120 megabytes. And then Red Panda, which is the smaller messaging queue, right? Red Panda also has 130 megabytes, right? So we have a messaging queue sitting in front, application sitting in the middle, and then the database sitting on the back end. And you can see the application in the middle is by far the smallest, right? So I think it's all the services that start up. And this demo is a little more complex because I have to send a message to Kafka. And how do I do that? I have to log into Kafka. No, not Kafka, Red Panda, I'm sorry. So I just copy and paste command here. So I log into this Docker image and go into this directory that I have set up with data, and then I send this JSON file into a topic, into a queue topic called order. Okay, so now I send it, and you can see here Docker Compose shows you the log. That's from one of the containers receives the message, and then from the WebAssembly container, it's the output a SQL string. So,
all right, so I'm going to totally pull this off because I always like doing this at the beginning of talks. All right, everybody say it. 3, 2, 1, 2. Okay, here we go. This is a great turnout. I'm excited to be here. So, quick introduction to myself. My name is Michael Irwin. As you can tell, I am from Docker. I'm actually in transition of roles at the company. I'm an engineering manager that's transitioning into the DevRel space. So we'll be helping re-kickstart our DevRel team. Prior to joining Docker, I was a Docker captain for 5 years here in a second. So it's designed from the start to be super, super fast. Okay? So lines and simulations, everything in a browser is mind-boggling. Okay? That's there. Adobe's been putting a ton of effort into WebAssembly, and so Photoshop, Lightroom, you can do that in the browser now, and it's using WebAssembly. Figma, how many people have used Figma before? Okay, how many think it's awesome? Even higher? Okay, Figma is a WebAssembly app. Okay, and Adobe just bought them for $20 billion. Okay, so that's pretty awesome. Okay, and I can compile it to this WebAssembly format. And then I need a runtime that can do that last step of actually, okay, let's turn it into zeros and ones that the CPU knows how to handle. Okay, it's got strong sandboxing, isolation, supports foreign language analysis. Was a number of people that were coming up to us and saying, hey, we're thinking about using WebAssembly in Redis, for example, and to be able to extend Redis so we can put basically a WASM runtime in and be able to do in-cache code. And so then you can do updates, or pub sub, or whatever the use case might be, but it's there in the cache, and so it's much more responsive. Also heard of other use cases, very similar to that. The Envoy service mesh is looking to extend the service mesh by using WebAssembly. So it's this idea, we're starting to see more of these use cases where WebAssembly is now providing almost a plug-in architect. They were starting to write their own specification of how to distribute these applications. Like, that's a solved problem. Okay. OCI, Open Container Initiative, defines specifications on how you build, share, and run applications. So why not piggyback on top of that? And so we want to do one quick demo of actually running a WebAssembly app in the browser. So I've got this application here. How many have ever played or written code to do Conway's Game of Life? It's a pretty common problem solving and learning to program. I won't go into it too much, but this is a simulation. Basically, I click play and it's going to run, and it's running at about 120 frames per second, which if you try to do that in JavaScript, you're not going to get that level of performance. Okay? So we kind of see it in action here. And one of the things that I wanted to do with Docker here was I wanted to set up a compose file where I'm actually doing I've got one service that's watching this WebAssembly code, and let's actually go in here and let's try to do something crazy. Let's double this, actually quadruple the size of our grid that we're going to be working with. And you'll see that when I save this, it's going to automatically recompile my WASM code down here. So the Rust tool chain and everything, it's containerized there. And when I go back to my browser, now it's much larger here. It's already been hot reloaded into my browser, and I just hit play, and now it's going. Okay, and that was still insanely fast, even with 120. Do I dare test my luck here? Okay, let's recompile. All right, you can barely see the play button down there. And it's still going about 60 frames per second here, okay? And so this is some of the performance, is that when we built the Docker file, the final container image, which he was shown was about 3 megabytes inside. What happens is when this this particular service starts, it's gonna extract the module out and basically drop it onto the WASM runtime. That's pretty much it. Okay? And so it's already been in Docker Desktop for ages now. Normally it uses container dshim and run C to set up all the kernel namespaces and control groups and everything else that's needed to start containers. What we've done here is we've created another shim that again does that extraction, and now using WASM Edge starts up the application on WASM Edge. Okay, but the cool thing is that they're all running side by side, and it's kind of that magical experience. The networking works as you expect, as we saw the demo here earlier. got a MySQL container running
Here virtually. Unfortunately, I was done with COVID. Got in at KubeCon, unfortunately, but yeah, happy to still be here and talk to you all. It's kind of weird that you all can see me, but I can see you, but that's fine. We'll get over it. So today we're going to talk about how to write better WASM microservices with Dapper. My name is Yaron Schneider. I'm a co-founder and CTO of Diagrid, a company that I co-founded earlier in the year. Before that, I spent 6 years at Microsoft, give or take, where I focused mostly on serverless container platforms that run at very large scale and open source technologies. They can consume Dapper really anywhere you can consume a container or a process. So Dapper doesn't have to be containerized, it can run as a process next to your application. And this is basically how it works. You have your app here on the left, the Dapper process on the right, and then you basically communicate to Dapper via HTTP or UC, and you get in state, publish messages, create event-driven architectures, pull secrets from secret stores. And the thing is with Dapper is that it doesn't replace your existing infrastructure, it integrates with it. And so we have over, I think, 108 components today, totally contributed by the community. So developers get these consistent distributed systems APIs, but as an infrastructure person, you can basically tell Dapper to target whatever infrastructure your company feels most comfortable with behind the scenes. So if you're running on AWS, you can target DynamoDB. Then if you want to move to Google Cloud, your code doesn't change. You basically tell Dapper, hey, work against Firebase, for example. When we launched Dapper, we only had 5 or 7 components. I think I wrote all of them. For the threading and networking primitives are basically, will improve in WASM. We'll be able to look at WASM as really a way to write these pluggable components. There's lots of things that needs to happen upstream in WASM to be able to do that. And currently, unfortunately, it's impossible for Dapper to use that, but this is really where we're going with pluggable components. WebAssembly is a stack-based VM. There's no security networking primitives. You're basically dependent on a runtime to give you access to that from the host, which means there's a very limited client ecosystem there. And of course, multi-threading. WASM has a great startup time, but once you have a WASM model that started, if it's long running or if you need multi-threading in it, there's very limited support for it outside of web workers who are really more compressed towards web type of scenarios and JavaScript. And if you have real simple scenarios like multi-processing of many events coming in, this is a host and this is a WASM runtime here, and this is a WASM module where my cursor is currently hovering. Then if you wanted to talk to Postgres, you couldn't just spin up a client inside of the WASM model and talk to Postgres. You would basically need to use something like an extension that's given to you from the WASM runtime that basically implements the driver in some way and has the networking primitives that you need. GP extension, you can just use a statically typed SDK for WASM from within WASM Edge, and this basically takes the networking primitive that WASM Edge as a runtime has and uses them to invoke Dapper. And there's a great demo of that online. You can search for it. I can do that for you and then just invoke your WASM module back with the events. Then this is a really great thing because we utilize the Dapper for the high performance, high throughput scenario. And we can also utilize the ecosystem that Dapper has.
Will be covered by Veron. So let's start. First of all, introduction. Yeah, I just here I will show the advantages using WebAssembly to run microservices. First, it's small, so if you compile your code, it will most of the time it will be a few megabyte size. And also, you can do high density deployment since the WebAssembly the code when you compile them, they actually you can in the runtime you can actually compact several of them into the single runtime. So this is running. So when the request comes, actually goes to the gateway and it's dispatched to one of the workers and start the instance. And we have we have agent running on each of the node code. Then you can pre-compile it ahead of time to native code. So after that, later you can load it. It can be inside of one worker, so that they are running in the same memory space. Actually, when they communicate with each other, we don't need someone else from outside to get involved. So in the originally when we call function A to function B, we actually, even if the function B is scheduled on the same node on the system,
and the user can directly see it on the dashboard. So this is one thing that we built. Second is on the shared memory. So whenever we have like microservices or functions, when they are communicating with each other, what is a typical RPC workflow is, first the service A or function A will serialize the data, then that data will be copied from the user space to kernel space. When it is copying, there is an interrupt and context switch from the kernel space. It will be like via NIC driver, it will be wired to another node. There also again it will go to the copy to the kernel space of the receiver. So first is lack of features. So right now we don't have garbage collection like Go routines for Go language. Right now open source so if I basically it's like compilation part. So if I take